Timberlake's Basic Chemistry, and we're in chapter 6.5 on covalent compounds and their names. Covalent means they're sharing valence electrons. The valence electrons are the last of the outer shell of electrons, and the subshells would be the s subshell and the p subshell together. So there's one orbital in the s with 2 electrons in it. There are 3 orbitals in the p, each with 2 in it. So that's 6 plus 2 is 8. So the octet rule, remember, is driving much of chemistry, which is that there's a stability in having an 8 valence electron pattern. So if you happen to be lucky enough to be an element in group 8, then you're already stable. Otherwise, you will either have to steal or get stolen from to achieve a noble gas configuration, or in this case, share. If you share an electron, then it counts for both of you. Now, the universe usually doesn't work like this. If I share a peanut butter sandwich with you, you're going to eat most of it, and I'm not going to share very much of it. But in the chemical world, if we share an electron, that electron counts for me and makes me stable if all I need is one, and it counts for you and makes you stable as well. So sharing an electron is a viable outlet for a reduction in energy for these elements. Okay, so let's look at this. When I said that a rock falls down the hill until it gets stable, okay, either till it gets to the bottom of the hill and hits the ground, or it hits a ledge, and whenever it's stable, it stops rolling. Same thing with a molecule. Increasing energy, in the case of, say, a proton, it's got lots and lots of energy. It wants low energy. It wants to be stable. Things fall down. They don't fall up. Okay, so what will happen is the energy of the hydrogen molecule is much lower than the energy of the proton, and consequently it's more stable. The lower it is in energy, the more stable it is. The more stable, the more it stays as an H2 molecule and less likely to react. The more unstable it is, the more likely it is for that element, or in this case ion, to react. Hydrogen protons are called free radicals, and if you've ever heard in nutrition what a free radical does, it's blamed everything from aging to cancer to everything else you can blame on it. So this example was hydrogen was as it shares those 2 electrons, each of those hydrogens becomes stable like helium. Okay, let's go back here a second. Remember, this is in group 1, and there's in that row, in that period, there are only 2 elements. There's hydrogen and there's helium. Helium has 2 electrons, but it's stable. In that first row, you don't need 8. It's an exception to the octet. You only need 2. And so by sharing 1 electron, hydrogen now has a configuration equal to helium, which is a noble gas. And this hydrogen also has a configuration of helium. Both of them are stable, and they would rather reside as an H2 molecule rather than as a hydrogen proton by itself. There are 7 of these diatomic molecules that are so reactive that they react with themselves. They don't just react with lots of other elements, but they react with themselves. Hydrogen being one, nitrogen and oxygen gas, fluorine and chlorine gases. Okay. Also in group 7 is bromine, which is a liquid. So bromine is a Br2 molecule, and then iodine is a solid, but it's an I2 molecule. So these are called diatomic. Anytime you see them in the free state, anytime, say, you are reacting something with oxygen, you don't just react it with O, you react it with O2, because free oxygen is always O2. Here's an example. What's the name of each of the following diatomic molecules? Okay, so we've got H2, okay, that's a hydrogen molecule. N2 is a nitrogen molecule. Cl2 is a chlorine molecule. All right, oxygen molecule, iodine molecule. So this is just the name of the element, but it's called a molecule. A molecule is going to have more than one atom combined together chemically. In this case, they're sharing electrons. Another very useful way to help understand the valence is to recognize that as they need 8, there's 8 in the valence, that these are called Lewis dot structures, or also called electron dot structures. And essentially, if you can think of the outer band of electrons as needing 8, then you can say, okay, carbon is in group 4. It must have 4 valence electrons. A hydrogen has 1. Hydrogen needs 2. Carbon needs 8 to be stable. So if hydrogen shares 1 of carbons, that hydrogen is now stable. And then all 4 hydrogens work that way. Now carbon has now shared 4 electrons with the hydrogens. Now carbon has 8. So the carbon has 8, it's stable. Each of the hydrogens have 2, it's stable. Now the formula of methane gas, CH4, is a stable molecule. It doesn't readily react. It does react. It can burn. You can see that methane gas is what is under your stove, but so it can burn, but it is very stable as a gas. It doesn't just immediately degrade. So if you're going to use electron, I think electron dots are very useful. So let's look, I know this is small, but let's look at the carbon in the first example. This is methane again. Carbon brings with it 4 because carbon is in group 4. Hydrogen brings 1 and it needs 2. So by each of the hydrogens sharing 1 carbon electron and the carbon sharing 4 of the hydrogens as they bring them, the carbon now has 8, hydrogen has 2 each, and so it's stable. Let's look at nitrogen. This is ammonia. Nitrogen's in group 5. So it has 2 on its own, the lone pair, and then 3 more that it can share with 3 hydrogens. The hydrogen then each has 2. The nitrogen then shares 3 hydrogens and then has the lone pair at the top. So that is in group 5. So you can see group 4 shares with 4 things, holds hands with 4 things. But nitrogen has plugged in one of those holes because it has 5 valence electrons, and so one of those hole spots is full. In group 6, you're going to see that 2 are full because it has 6. So there's 2 at the top, 2 on the side, 1 on the bottom, 1 on the side. Each of the ones can share with a hydrogen. The hydrogen now has 2, it's stable. The oxygen now has 8, it's stable. And now you have the configuration of water, H2O, with 2 lone pairs. Why is there a lone pair? Why are there 2 lone pairs? Because it's in group 6. It brought 6. It only needed 8, so it's going to hold hands with 2 things. Okay? You're going to see it's the same thing with group 7. Group 7 already has 7. That means it has 3 lone pairs, 3 arms are already plugged. 1 is free. It can share with a hydrogen, so HCl would be hydrochloric acid, or HF, hydrofluoric acid. That would be 1 bond. So group 7 can hold hands with 1 thing. Group 6 with 2, group 5 with 3, group 4 with 4. Now, the names. The names are what drives everybody crazy with covalence, because the problem is that these nonmetals with nonmetals are mainly forming the covalent bonds. The ionic bonds are formed with a metal, something on the left side of the periodic table, joining with something on the right. And you would just name it sodium chloride. Okay, sodium because it's the furthest to the left, you just name it according to its element name. And then the nonmetal, normally with an IDE ending. We've seen with diatomic molecules that you can have things like ates, okay, carbonate and sulfates. Those are when a nonmetal joins with oxygen and becomes itself a polyatomic ion that can then join with one of the metals. Well, in the case of a metal with a nonmetal and a nonmetal, the problem is you can have more than one combination. Look at the idea of nitrogen and oxygen. Both are nonmetals. You can form viable NO, nitrogen oxide. You can name it NO2, where there's a different one. You can't call that nitrogen oxide because you already have something with that name. And now you have an N2O. You can't call that nitrogen oxide. You can't call all 5 of these nitrogen-oxygen compounds nitrogen oxide. Because they make more than one possibility, you have to name them a little bit differently. With an ion-ion bond, an ionic bond, they make one possibility. So you can ignore all the subscripts. You don't need to worry about it. So when you have Al2O3, you just call it aluminum oxide, okay? Because there's only one possibility of aluminum joining with an oxygen ionically. But if you have a nonmetal, remember nonmetals are anything to the right of the stairs, a nonmetal with a nonmetal can form all kinds of different compounds, multiple compounds. All right, you saw that in the polyatomic ions with nitrate, nitrite. Remember, you had chlorate, perchlorate, chlorite, hypochlorite. There was 4 of those. So for that reason, nonmetals with nonmetals have to have a different way of naming. You're going to use the Greek counting to 10, the numbers in Greek 1 through 10. Okay, on the side here I've got them. 1 is mono, 2 is di, 3 is tri, like a tricycle, 4 is tetra, 5 is penta, pentagon. A lot of your math things use these Greek prefixes, so pentagon, hexagon, hepta, okay, that's 7. Octa, you would know octa like an octagon. Nona is 9, and deca is 10. So if you have something that has more than 1, you'll call it di, tri, tetra. If you have something that's 1, you usually call it mono. Okay. Now that would be with the exception of the first one. If you were to say 1 nitrogen and 1 oxygen, okay, you would just call that nitrogen, and then the oxide would be monoxide. Nitrogen dioxide, dinitrogen oxide, dinitrogen tetroxide. Okay, so the only real weird one that you have in terms of whether to use it or not is mono. Usually do not say mono for the on the first element, just the one to the right, to the farthest to right. So in this case, you could say carbon monoxide, carbon dioxide. Okay. There's some spelling things because you've got all these vowels shoved together, so sometimes you can just say tetroxide rather than tetraoxide. Okay, so there's some weird things here. But you're going to use these Greek prefixes for the first and the second term whenever you have nonmetals with nonmetals. Okay, so let's look at some examples. CS2, carbon disulfide. Now let's go through them again, and you may want to go back and write these down. Mono is 1, di is 2, tri is 3. Okay. Do we have any others? There's a 6. Hexa is 6. All right, so let's look here. So we have CS2. So I need a di on the sulfur. So it's carbon, disulf, and then it ends the same as you learned, ide. Carbon disulfide. Okay. Here's CO2. Just name the first one carbon. You don't need to say monocarbon. Carbon. Then it's di. Then oxygen goes to oxide. So carbon dioxide. Okay. Nitrogen oxide, or you could say nitrogen monoxide. N2O. Dinitrogen oxide, or dinitrogen monoxide. SO2. Sulfur dioxide. Then 3 is sulfur trioxide. And then SF6, sulfur hexafluoride. Okay, let's do some examples. Select which one would be right for A. SiCl4. Okay, well, if there's one Si, so it can't be tetrasilicon, so it needs to either be 1 or 3. Then I have 4 chlorines, so it needs to be silicon tetrachloride. So A would be number 3. How about P2O5? So I have 2 phosphoruses, so I need diphosphorus pentoxide. Now notice that's pentaoxide and the A drops because of the vowels, pentoxide. diphosphorus pentoxide. Cl2O7, dichlorine heptoxide. Okay, the A drops because of the vowel smearing. Okay, same as we've said before. What's the first one? Carbon monoxide. Number 2, carbon dioxide. Try to do it right before I do it. Phosphorus trichloride. Carbon tetrachloride. Dinitrogen monoxide. I think it could also say dinitrogen oxide. Write the correct formula for these. Phosphorus pentachloride. Okay, well, phosphorus doesn't have a di or tri, so that means there's one of them, so it's P. And now I have penta, which is 5 chlorines. So it would be PCl5. Okay, dinitrogen trioxide. Well, here's a di, so that's 2, so I have 2 nitrogens, so it's N2 trioxide, 3 oxygens. So N2O3. And the last one here, sulfur hexafluoride, S, and then hexa means 6 fluorines, SF6. Identify each compound as ionic, covalent, and give its name. Okay, so remember, if it's ionic, you've got a metal and a nonmetal, something on the left and something on the right, and you ignore all of its dis and tris and hexas. Okay, if you have 2 nonmetals, anything to the right of the stairs, you do have to do the Greek prefixes. All right, so let's do the first one, SO3. All of these are nonmetals. That means it's covalent, and I have to use the Greek prefixes. So I'm going to start with sulfur. Don't say monosulfur, sulfur, and now trioxide. Okay. Manganese and chlorine are as a metal and nonmetal, so that's ionic. So I ignore the 2, ignore the 1, and just say manganese chloride. C, these are polyatomic ions. NH4, remember, is the only positive one, and it's positive 1. And PO4 is phosphate. And so ignore everything, and you just call it ammonium phosphate. Copper does have to be named because the CO3, the carbonate, is -2, and that means that it takes 2 somethings to bond with a -2. That means it has to be 2 positive 1s, so this is copper 1. Copper 1 carbonate. Okay, I'd call that the hard one. Then nitrogen and oxygen are both nonmetals, so this is covalent. Dinitrogen, tetraoxide, and then drop the A, tetroxide. Dinitrogen tetroxide. Last one, identify ionic, covalent, and give its name. All right, so you have calcium and phosphate, so it's calcium phosphate. Bromine is in group 7. That means that's -3, so the iron has to equal that, so it's iron 3 bromide. And then sulfur and chlorine are both nonmetals, so that's, you use the Greek prefixes, sulfur dichloride. And then chlorine and oxygen are nonmetals, so it has to be dichlorine monoxide or dichlorine oxide. I would say monoxide. Okay, just keep a going, keep a going, keep a going. Summer's coming.